If need be, there's a reload meeting materials button in the top left.
Reload meeting materials in the top left.
If you go to the meeting materials, then there's a...
Aha, yes, I see. Yeah. Yes, now it's showing up.
Okay. Yes. So I'll start now with the note well, as people might slowly be filtering in. So first, hi everybody. We're going to have a talk given by Mark Kaplan from VeriCloud. But before we get to that, I'm going to go through the note well. I'm going to kind of leave it on the screen as usual and go through the slides for you to just slowly absorb them. This is a recorded session. There's a reminder of that at the bottom right. And yeah, just to wrap up the NotWell IETF is the research organization, not a standard organization like the IETF. So do keep that in mind. Our focus is fostering collaboration and talking about research. With that said, I'm going to introduce our speaker. So our speaker for today is Mark Kaplan. Mark Kaplan graduated from the University of Paris-Sud, and he has worked in Montreal with Gilles Brassard and in Edinburgh with Ilham Kashefi. And before founding VeriCloud, his research was focused on using quantum algorithms to break classical cryptographic systems and on the design of quantum resistant alternatives. And Mark is from VeriCloud, which is a startup based in Paris. It's founded by Mark, Ilham Kashefi, and Joshua Nunn. Its focus is on developing solutions for long-term security based on quantum communication networks. In particular, it has developed Q-Line, which I will let Mark talk about today. So that's it. I will stop sharing my slides. And hi, Mark.
Hi, Wojciech. Hi, Rodney. Hi, everyone. Thanks a lot for the invitation and the introduction. Can you hear me well? No problem.
Oh. Yes, I can hear you now.
Perfect. Okay, so I'll now share the slides. Right, these are the ones. All right, so I'm going to present.
Mark,
yes?
Sorry, just before we start, are you okay with questions during the session, or would you prefer if we leave them for the end?
No, during the session is fine.
Okay.
It's fine. Yeah, it would make things more interactive. So no problem.
Okay,
right. So I will present our work at VeriCloud. Actually, what I'm going to present is the core of our work. But I want to start with a quick intro about who we are and what we're doing. I'll talk a bit at the end of more longer term goals, also in terms of research. So as it was said, we are a startup based in Paris. We work in quantum networks. These two people, Josh Nunn and Ilham Kashefi, are my co-founders. All three of us, I mean, Josh and Ilham work in academia. I have an academic background, but I've transitioned to VeriCloud a few years ago. And the ambition that put us together is that quantum communication is, of course, a great realization. But in order to transfer what we knew about the technology to the industry, we believed that there was a lot of work to be done on the software level. Right? It's not only about building better and better devices, but also adapting those devices to match specific use cases, right? So everything I'm going to tell about is new work that we performed at VeriCloud, but just keep in mind that we don't do anything new regarding the physics there at VeriCloud. All of our work is on the abstract layers of quantum networks, and of course, one important thing, I talk about it at the end, is that we're driven by this long-term vision that, of course, everybody there likes a lot of building a quantum internet, so a global quantum network, and especially the work of Elam on secure quantum cloud computing was a strong driving force to start VeriCloud in the first place, right? So as I was saying, this is the core of our work. But we also participate to a few research projects, including the Quantum Internet Alliance. So if you're interested into partnering through research projects, don't hesitate to contact me. All right. So these are actually all the people that are involved into this work about Q-Line. Although we've been developing this architecture for a long time, the paper summarizing all the results is still under publication. So Josh, Elam, and I worked on the core idea and the realization. Georg here is the photonics person in charge of the application, and Anne and Mina work more on the security proofs and software aspects. Right. So probably one thing that I don't have to tell here, but I like to remind to people when I talk about quantum technologies, is that quantum networks is already a rather mature field, in the sense that we can find quantum networks in the world. Some of them already exist, some are in development. The main one, or the most important one today, is the Chinese quantum communication network. In Europe, there is a strong push toward this European quantum communication infrastructure project, with lots of local initiatives now being built, local quantum network. By local, I mean at the scale of a city, for example, and connections between them using satellites. Right. So when we talk about quantum technologies, and in particular quantum computers, we're talking about something that is long-term. Quantum networks are still at the beginning, I would say, but it's something that is happening now, as you all know here. But it's always good to remind it to audiences in general. Right, and why do people do that? So this is a very short summary, of course, a summary of years and years of research, and also I'm summarizing the story more from the user point of view, or the customer point of view, I should say. Of course, with quantum key distribution that you can run on quantum network, you get this unconditional security, which implies, I mean, it has lots of very nice implication. Your data you can guarantee the security of your data for very long term. Which becomes more and more relevant since the value of the data has soared over the last decade, I would say. One thing that is really cool is that you can use quantum key distribution in combination with symmetric cryptography to make it more efficient. And I don't think that's downgrading the security. It's not unconditional anymore, of course. But what you get in the end is a quantum safe system using, I mean, for the encryption part, using only standardized algorithms, which I believe is somewhat a very interesting feature of QKD, quantum key distribution, right? And other consequences, you can prevent data harvesting, all the attacks of the type of storing now, break later. And it changes the way you can think of encryption in general, right? So whether you believe that this is important for your use case or not is debatable, but there are some advantages, not only theoretical but in practice. When you deploy QKD, you can have these advantages. But now, of course, we're talking about quantum technologies, and as always, the main issue with quantum technologies is scaling. Here, by scaling, we're not talking about having more qubits, but having more nodes in the network. And the way QKD networks are scaled today is a little bit embarrassing, in the sense that it's very expensive, because QKD is a point-to-point task. So when you want to add more nodes, you add more point-to-point or more edges, in fact, to your network. And also, in order to distribute keys in your network, what you do in general is using trusted nodes to route keys. I'll talk more about it later. And trusted nodes inject vulnerabilities into the system, right? So these are big drawbacks of when scaling quantum key distribution to the network level. Right. So what we do at VeryCloud, we wanted to address very specific use cases for quantum key distribution, and what we came out with is a novel quantum network architecture. And with this architecture, the goal is not to develop a nationwide network, but network it to do quantum networking at the local area scale, or I would say local or metropolitan area scale. We'll talk more about the scale later. But I like to think about it as a quantum Ethernet, because in fact it's also very reminiscent to the very first version of the Ethernet protocol in terms of architecture. And in this very specific regime, so local or short distance, what we get is with the Q-line is a fully connected quantum communication infrastructure, meaning any pair of nodes can communicate securely or establish keys, in our case, without using trusted nodes. So this is the first property. Then also the scaling is somewhat better, because we don't use we use mostly standard telecom components rather than as opposed to quantum specific components. As you will see. And also, because we have this long-term vision, we were also talking about connecting these architecture to quantum computers. I'll show you how this can be done at the end of the talk. All right, so what I want to show you today is what is the Q-line protocol. It's an architecture with a protocol. Again, everything happens at the abstract level. What we can show or what we can say about the security of Q-line, how you prove security in theory and what it means in practice, and then discuss the use cases for today and for the future. All right, so it's a good time to stop and ask if there are questions before entering into the technical description of the protocol, or the somewhat technical description of the protocol. If not, I can. Sorry, Stephen.
Oh, wait, let's see. Looks like there's a queue up.
Yeah,
Stephen, you want to ask?
Yeah, you can hear me, right?
Sure.
Yes.
I just want to ask, it's not like a token ring scheme, right? It doesn't go all the way around.
Well, you'll have the answer at the end of this series of slides.
Okay, no, wait, thanks.
So the way, I mean, there are multiple ways of introducing the protocol. The way I like to do it is, well, first it's at my very computer science-y level. I'm not going to talk again about physics in this talk, and compare it with the standard QKD. Right. So one way of thinking about QKD is on the left here. You have two parties, Alice and Bob. And you can think about Alice generating a quantum state, a qubit, and encoding some information in some basis in this quantum state. These are the role of these two operators, X and H. And then sending this state to Bob. Bob chooses, performs these two operations. He chooses a measurement basis for the qubit. This is the role of this operator H, and then performs the measurement. And if you write everything down, you can have that the mathematics tell you that if they chose the same basis, meaning R equals S, then A is the measured value by Bob, right? And based on that, you can derive the whole protocol and security proof. So one way of thinking about Q-line is just decoupling these operations. In Q-line, what we do is rather simple. I introduce these two parties in the middle, Charlie 1 and Charlie 2. and I would redistribute the roles. Alice generates the qubit again, sends it to Charlie. Of course, the qubit is a photon in the standard implementation. Charlie encodes the information and chooses a basis. Charlie 2 chooses the measurement basis, and Bob performs the measurement. Right, so at this stage, you can't do much because the result is known by Bob only, and if he announces the result, then well, everybody would know what is the secret key. But oh, here it is. The fix is very simple. It suffices to re-inject some randomness, right? So, oh, sorry, I should precise here. The goal is for C1 and C2. So let me go back here. C1 and C2 want to establish a shared bit in this case. So if Bob announces the bit A, then everybody would know it, and not only C1 and C2. But the fix is quite simple. It suffices for C2 to re-inject some randomness with this operator x to the b here. And now what Bob announces is the parity of the two bits, A plus B. And of course, A is known by C1, and B is known by C2. So if A and B is broadcasted, then C2 can also derive A, but as long as he keeps B private, no one else knows the value of A. I see there's another question here.
Scott, would you like to ask your question?
Okay, let's continue. Anyway, the protocol has a few more steps. And if the question comes, I can interrupt again. Right, so this the role of this x to the b here is to re-inject some randomness into the information to keep it private to C1 and C2. And in fact, it's very easy to see that this is still not secure, and you also need, in fact, to inject randomness at all of the stages of the protocol. So A would start with a random state, random BB84 state, for example, or from the same state set of states C1 and C2, and the rest of the protocol follows as long as you take into account the required corrections. Yes, Wojciech?
So the question was asked in the chat, so I'm just going to read the question. Scott asks, who selected A and B? And there's a similar question, so I might as well read it straight away, and who selects R and S?
Yes, so the selections are made locally, meaning C1 chooses A, which is the bit, the random bit that would be the key in the end, and R is also the basis of encryption is also chosen by C1, but they are kept private. They are not broadcasted. And similarly, C2 chooses B and S here, right? So at the end, they can just select on. So at the end, after all the measurements are done, they only keep the bit if R equals S. They chose the same basis, and in this case, A plus B is the result of the measurement. This is broadcasted. So of course, if you want to use A as a secret bit, then C1 already knows A, and C2 can derive the value of A from B and A plus B, of course. So it's just as long as all the data are kept private, you can broadcast this A plus B in the end, and it allows only the legitimate parties to learn the shared secret bit, which is A at the end.
And the follow-up question in the chat is, who is C1 and C2? Are they intermediate devices, or are they subcomponents of A and B?
No. Sorry for the misunderstanding. These are new intermediate nodes that we are putting in the network. Now, so my goal here is to build a network from a QKD network. So QKD is point-to-point. Here I'm adding more nodes to the network. So in this example here, I have a 4-node network with Alice here, Bob at the other end, and C1 and C2 in the middle. Charlie 1 and Charlie 2 are intermediate nodes. The reason I keep A and B at as extremal points is because they will be, in terms of information processing or what they can do physically, they are equivalent to the Alice and Bob of QKD, right? Whereas, as we will see, C1 and C2 are much lighter in terms of physical components required to implement them. Right, so I have a 4-node network. I started, so to say, from A and B, which are standard QKD devices, and I added to the network these 2 nodes, C1 and C2. All right, so a very rough picture here is, if you want to think about the components or the costs, as I was saying, the extremal nodes are the same. So in Q-line, my Alice is composed of laser and modulators. The Bob at the very end has this very specific and costly component, very specific for QKD, which is a single photon detector, right? So when I want to build a QKD network, I have to put all those components at all the nodes of my network, whereas with Q-line, the intermediate nodes are just standard photon modulators. This is a standard piece of telecom component, and literally something that you can buy online by drag and dropping it to your cart and pay with your credit card, right? Which as far as I know, you cannot do with single photon detectors, for example. Now the counterpart is that, as I was saying, this is not a replacement for QKD. It's a different regime because in a standard QKD network, I would have around, let's say, 100 kilometers between each node, whereas with Q-line now, it's the distance between the laser that emits the photon and the single photon detector. At the end, this complete distance has to be roughly 100 kilometers, right? And I'm hiding a bit of details because all the modulators here might or will induce a little bit more noise. So the more nodes you add to your system, the shorter the distance you can reach will become. So it's a trade-off between those 2 parameters that you can reach. Let's say that 4 to 5 nodes is the normal regime for Q-line, but it's very good for some of the use cases that we want to reach, as I will explain. Or it's good enough for the use cases that we want to reach. All right. The first remark: people that have been involved into QKD networks might, already see that they don't work the same in terms of key establishment, right? What happens in QKD, in a QKD network, is that each pair of devices will establish a shared key, or each pair of adjacent devices or connected devices will establish a pair of key, and everything will happen in parallel, right? So here, if I sort of keep the same topology, I have Alice, Charlie 1, Charlie 2, and Bob. Remember, these are QKD devices, so they can do single photon measurement and encoding, decoding, everything. So I would have at a given time bin, I would have a bit or a shared key, let's say, established here and in parallel here and there, right? So it seems that it seems very, very, very good or very efficient. But now the thing is that in practice on a QKD network, you will also want to establish keys between non-adjacent devices, and for this, you need to use key routing. Key routing is just done by choosing a key at for example, Alice, sending it encrypted to Charlie 1, and then Charlie 1 decrypts, re-encrypts, and transmits to Charlie 2. And this is how Alice and Charlie 2 would establish a shared key, which is in this dotted arrow, the first dotted arrow on top here. So this pink dot in the middle means that Charlie1 is in fact a trusted node in the sense that you will get a clear copy of the key that is established by Alice and Charlie2. But also another important thing is that sending or routing the keys to non-adjacent parties will also consume some of the primary keys, the keys that were established in the first place, right? So I have of course, I have an efficient system in the sense that all the key establishment happen all in parallel. But on the other hand, when I want to route keys to non-adjacent parties, I need to consume the primary keys, right? So what happens on Q-line is that we simply use some round robin scheduling, for example, or we use time multiplexing. It's a better term, by giving to each pair of nodes a dedicated amount of time. The protocol that I showed you earlier allows the Charlie1 and Charlie2 to establish keys, but if you want to have keys between Alice and Charlie2 or Alice and Charlie1, you just leave the other devices passive during this round. So it's not a big deal. I mean, the previous protocol captures the core of the key establishment on Q-line. And so it seems much less efficient in the sense that not everything happens in parallel. Roughly speaking, there is only one detector, so it can only be used by one pair of nodes at the same time. And while this pair is establishing a shared key, the others have to wait. But now in the counterpart is that there is no key routing, right? So this, while the number of pairs grows quadratically, you don't need key routing. And once again, whether it's good or better than QKD, I don't think it's the right way of assessing this question. You need to look at very specific use cases. But what we can show is that under following assumptions, that the keys are uniformly distributed among pairs of nodes, meaning each pair of nodes equally need key establishment, and that the cost of the system is dominated by the cost of the detector, then the price per bit of key is the same as with QKD, right? So Q-line and QKD with this figure of merit under these assumptions are comparable, right? But once again, it depends a lot on what use case you want to choose. You want to solve if you want to make a precise comparison, a more precise comparison. How about security? So the security of Q-line for the theoretical part, I wouldn't say it's easy, but it's as easy as you can think of. We have, and it took a lot of time to get them, but we have good frameworks for proving the security of QKD. And in our case, we rely on the work of Thomas Miquel and Leverrier for proving the security of quantum key distribution. And so in my example here, I only have one center node, but it's the same. I mean, it's the same for when you add more and more Charlies. The goal is to show that if you can attack the Q-line protocol, then you also get an attack on the standard QKD. Right, and the reason, based on the protocol, it's quite straightforward, is because at all the steps of the protocol of Q-line, this is how it's designed for sure, and standard QKD, an eavesdropper will see exactly the same state. Right, so this is the core idea. Now, of course, translating it into a formal scientific argument takes like half a dozen pages, but this is exactly how the proof works, or the core argument of the proof. Another very important chapter of security in the world of QKD are the side channel attacks. So that we know that there are differences between the the mathematical model of QKD and its implementation with physical components. And in fact, you can exploit those discrepancies to attack it. Well, of course, we have all the QKD, the side channel attacks of QKD that still hold in our case, but since the extension of the QKD protocol to a Q-line protocol happens at the qubit level, all the physical implementation is compatible with what we're doing. So in particular, if you want to use decoy state protocols, it's still possible with Q-line. It doesn't change anything. Now, there are other types of attacks that are possible. In particular, I'm talking about Trojan horse attacks that consist in injecting light into the system for the eavesdropper to try to measure what's happening in Charlie. These are things that we can prevent with very standard techniques. But there are also more, I would say, elaborate attacks relying on non-destructive photon counting, so some devices that are much more difficult to build today, and as far as I know, are not commercially available. So this is, we're still performing some research and development in order to close these attacks that might be available in the future for future eavesdropper. All right, so this was the theory part of the theory presentation of Q-line protocol and security. What I want to spend the second half of the talk is to present you why we think this is a good architecture, or I should say, in which case we believe that this is a good architecture. I'll also use this to answer Stephen's questions, or to make a remark, a follow-up remark. So the first application that we are thinking about when using Q-line is how it integrates in global quantum networks. So you remember that when you want to scale quantum networks or QKD networks, you usually, what you do is just using key routing to route keys to non-adjacent parties. So these connections happen at the software level, right? So Q-line is compatible with any other QKD implementation in the sense that you can combine them all together to build a large-scale network. And this view here, it's an artistic view, but this is the work in progress in this EuroQCI project, European Quantum Communication Architecture. You see that there exist several layers with satellites. Probably locally you would have a backbone, a high-speed backbone. And what we do with Q-line is the last kilometer or last mile of the network. How to distribute the keys at the local area scale. So we are deploying this architecture, testing in real field now with Deutsche Telekom in Berlin. It's actually more involved than that. What we want to do is show that Q-line can be used to build complex metropolitan architecture. It's just one building block of the global network. So yes, it is a token ring. But you can also use it in combination with other techniques to build complex networks. And in Paris, for example, Orange, the French telco, is building a quantum communication architecture at the Paris region level, and Q-line will be deployed at the level of a city that has several critical infrastructures in the south of Paris. Yes, Wojciech?
So I'm going to transcribe a question from the chat, which is, QKD networks with trusted nodes can be built without optical switches. Is there any advantage of Q-line compared to that? Wait, without trusted nodes.
Yeah, I'm trying to.
Sorry, I'm gonna clarify the. I guess the question is, QKD networks without trusted. Okay, sorry. QKD networks without trusted nodes can be built with optical switches. Is there any advantage of Q-line compared to that? That's the question.
I guess. I mean, I'm not sure what this. I mean, the way I see QKD networks without trusted nodes is by using repeaters, but I'm not sure what this is what the question.
No, I think the question implies that you can just route photons, I guess, with an optical switch.
Yes. Okay. Yeah. No, I see. No. So that again, this is the, how can I say? This is a technique that can also be used in Q-line, right? So the advantage that you still have is that you can add nodes using only standard telecom components. But once again, I mean, again, the standard modulator, the photon modulator. For example, if you use polarization encryption, this would be polarization modulation. So you can also combine it with this technique of using optical switches. As far as I understand the question. So
there's a follow. In case we're running out of time, we can leave some of these questions for the end. By the way, Mark. So just let me know if you have a lot of material.
Well, not so much, and I can also go fast at the end. No worries. No, I'm interested in this question about the core architecture, actually.
Yeah. So Stephen, as a follow-up to that question, suggests that he thinks also the Q-line versus optical switching provides higher connectivity. Is that correct?
Expand a bit. I just mean, like, in the diagram, the connectivity was like a completely connected network, where optical switching with the routing maybe doesn't give the same thing. It's like
No, I think I see what it means. Would be interesting to compare it for a specific network topology, for example, or a specific use case. You know, how you can take advantages of this fully connected architecture. For example, I'm going to show an example of usage in a moment, and this is something that can be, as far as I understand, realized exactly the same with optical switching. So I'm going to show an example where there is no advantage of Q-line over optical switching, but yeah. Might not always be the case. I mean, not the second one, actually. So let's try to see if these questions make sense for the next two examples, or if we can say something.
There is a slightly unrelated question, so I'll ask it made as well. Just can you expand how Q-line would work on a fully quantum network, one that shares entangled qubits? What advantages would it have over simpler approaches?
Transform. Okay. I'm not sure I can say something about this right now, but this is so for over a full quantum network that can transport entangled qubits, you could also have intermediate nodes. I'm not sure in which case it's interesting. Right? You could ask the same Charlies, but I'm not sure in which. Something that we need to.
My guess is the implementation complexity. It's just maintaining entanglement. You don't need quantum memories, for example, in any of the Q-line implementations to start with. That's already a huge simplification. So I'd say it's mostly just the stage how advanced your networks are.
Yeah. So I'm going to show an example at the very end where it's interesting in the furthest term networks. So even beyond quantum entanglement, but for the specific of for the specific question of entanglement, I don't know.
Okay, that's all the questions in the chat for now.
Okay,
Thanks.
thank you. Thank you. The second example, the second use case is for secure storage, right? We know that it's not something that we invented, but we know that it's possible to combine quantum key distribution and classical cryptography to protect not only communication, but also storage. And a full specification of the protocol was given in the paper quoted here, and I think it's a beautiful idea by combining QKD with a secret sharing scheme that distributes those shares here over several servers. You can get very highly secure storage. The classical cryptography protects against data leakage. You can ensure that corrupting one server is not enough to recover the original data. And in fact, the number of servers that need to be corrupted is very easy to parameterize in this system. With the quantum communication, you protect against data interception, and by continuously re-encrypting the shares, you can make sure that an eavesdropper that wants to learn your data needs to attack several servers within the time slot of re-encryption. Right, so it's a very strong idea. The only thing that the new thing that we bring here right now, what I can tell you is that Q-Line, since it doesn't have trusted nodes, it also has less vulnerabilities. So it's just a better way of doing it, and it's also compatible with, for example, the notion of the concept of cloud availability zones. That usually, when you store your data to the cloud, they are distributed on several servers, all in the same metropolitan area. So it's the right scale for deploying Q-Line. Another thing, but it's still also, it's not only a research topic. It's known that this secret sharing, it's known that some secret sharing protocols also, it's possible to compute on top of shares, so you can run some computation with some overhead, of course, to compute on the shares without reconstructing the information, without recentralizing the information, which would be a security breach. So you can use secure multi-party computation for that, but also I want to stress that a very similar architecture was introduced in research papers similar to Q-Line in order to do secret sharing, classical secret sharing protocols. So it seems possible to do some computation assisted with some classical computation assisted with the quantum communication, right? Quantum communication, classical computation, quantum assisted classical computing. This is what I wanted to say, right? So here you can really take advantage of the fact that you have a fully connected network, and this would be an interesting place to compare with the switching argument that was asked previously. Okay. Last but not least, another application that we just putting forward when we talk about Q-Line in practical environments, it's a very practical question again, right? So suppose you want to build these global quantum networks, you would have at some point an interconnection between the two networks operated by two different operators, right? So you have your first network on the left, second network on the right, and if you want to make this connection, you have to rely on a trusted node here in the middle, and the dotted line here says that the trusted node is operated by the operator of QKD network 2 on the right, but it's actually an issue, right? How do you know, or how do you establish the trust between the two operators? They might have different standards on what trusted nodes are and how they are implemented in practice. here it's just a completely straightforward application. I build two queue lines that overlap, right? And now I have two routes to two independent paths to route keys without trusted nodes, right? The green one and the blue one here are completely independent. So now I don't rely on the trusted node anymore, in the sense that if an eavesdropper wants to learn the key established by network 1 and 2, they would have to attack the two nodes on the left and on the right. Right. So it's a very straightforward application of or straightforward consequence of the fact that we can have multiple paths using Q-line, but for a practical problem. And my understanding now for this problem is that there will be no advantage over switching, as it was mentioned earlier, as far as I understand the technique. All right. Just to before concluding, another thing that we are investigating, which is more for this future applications, is the connection with quantum computers. And one thing that people here might know, or otherwise I'm just reminding very quickly, is that once you can connect quantum computers to networks, you unlock secure quantum cloud computing. And by secure here, I mean verifiable and blind, right? So in the picture here, you have a quantum computer and you have a distant party that, okay, I'm cheating a little bit here. I'll just explain the details on the next slide, but with a device that is somewhat similar to what QKD is doing today, it can delegate the computation to the server with blindness, meaning the server does not learn the computation it's executing, and verifiability, meaning that you can detect the deviations from the original computation. Right. This is the work of many people, but in particular, I have to quote my co-founder Hélène Cachefi for her work on verifiable blind quantum computing here. And now you remember that with Q-line, we started with two devices that are similar to QKD as well. And in fact, it's easy to see that you can do the same here to delegate your quantum computation. You can, rather than starting from QKD, you start with Q-line and you replace the end node, one of the end nodes, with a quantum computer, as if it was easy to do. And then what you have is the ability for multiple clients to delegate their computation to the server, right? So what we get is a somewhat scalable architecture for secure quantum cloud application. You can also run some distributed quantum computing on this with this type of architecture. Now, the only detail, I would say, in addition to having a quantum computer, is that first, it's not known. When I said here you start from a QKD device, you know that in practice QKD devices, especially the part that emits the photon, can be done very easily using attenuated states. It's not known that you can do it with attenuated state for secure quantum cloud computing. So you might need true single photon generators, which are not easy to build. And in order to connect your quantum computer to the network, you might need, for example, this looks very much like superconducting qubit, so you might need some frequency conversion, which is also difficult to implement. But at the end of the day, these devices, I believe that they are simpler to build than a quantum computer in the first place, right? So there are lots of details in the implementation, even you know, if the research or the development of quantum computers is doing well these days, there is a lot more to do to get this kind of application, right? So this is exactly well, this is one of the things that we spend a research effort on, is to try to show that this vision that we have is possible in practice. Okay, so let me conclude here. I introduced this architecture, the Q-line. We like to think about it as a quantum Ethernet. It's using these this scalability with standard telecom components. So it's possible to well, we get, let's say, a better node connectivity for a given cost in the network. This architecture is scalable in the sense that we can add. It's easier to add more nodes in the system, and also secure because it's not using trusted nodes. We get some. We have proven the security. And also, I mean, it's still work in progress for more futuristic attacks, but we consider the side channel attacks. I have introduced some application and this very cool vision in the future that also we can use it in combination with quantum cloud. With quantum computers to perform secure quantum cloud computing. So this is sort of the roadmap that we have at VeriCloud. With this EuroQCI, but also initiatives outside of Europe, we have a very nice playground for secure communication. We can deploy these hardware in all the quantum communication networks that are being built today. Secure storage is something that we are already developing with the hope of showing how Q-line can be used in a real implementation, let's say at the beginning of next year. We are also developing and researching on how to compute on top of these stored data by running mostly classical, I mean, for classical computing, but also quantum-assisted classical computing. And the long-term vision is that all these things should evolve toward a quantum internet where we will be able to run these algorithms that were developed for secure quantum cloud computing. Thanks a lot, everyone. I hope this was interesting to everyone, and we have some time for questions.
Thank you, Mark. So first, I guess, a digital applause. Thanks for the talk. And now, as Mark asked, floor is open to questions. So please ask your questions. Ideally, you could raise your hand and ask them with your microphone. But if that's not possible for you, try the chat. But you will likely get a faster response by raising your hand and asking with a microphone. So actually, Rodney started. So Rodney, I guess go ahead, ask your question.
So thanks, Mark. This was a really interesting talk. I'm not sure what limits the scalability of the system you're designing. You initially presented it as LAN or maybe metro area scale systems, but I'm uncertain what limits the internode distance and the maximum number of nodes you might use.
Well, I would say, as always with quantum communication, the limit comes from the losses in the fiber, which, you know, apart from being very careful with the fiber, we cannot do much. So ultimately, this distance here is limited by. I mean, the limit is the distance between the first node that emits the qubits and the last node that measures the qubits. Regardless of the number of intermediate nodes, you have an inherent limit. But also, in addition to that, each of the intermediate nodes, they add some losses to the systems. And here, well, the best you can do is do very, very nice engineering, but well, I guess we will always have some losses that will decrease the maximum distance that we can get with the system.
So your modulators here are just they're modifying the photons, but they're not regenerating the photons.
Yeah.
Okay, so that means that your end-to-end, your left-to-right limit here is single photon in fiber transmission limits. So that's 100 kilometers or so. Okay.
Right. But the number of intermediate nodes now is limited also by the fact that these modulators, they are not perfect, and they also induce some loss to the system.
Makes sense.
Well, not really the modulators, but the connection between the fiber and the modulation.
Yeah, the fiber couplers and whatnot. Okay. Thanks.
Stephen?
I just
You
want to
have your
ask,
hand raised.
do you think there's advantage if some of the like the intermediate nodes have the ability to detect? Like, do you get maybe more robustness or something? Maybe it's more expensive though, but
yeah, well, yeah. So you get advantages also for the security. For example, these side channel attacks. But I guess if you add a modulator, this would be if you add a detector at the intermediate nodes, this will be also very similar to the switching that was mentioned earlier.
yeah, maybe like, okay, makes sense. All right, thanks.
Thanks, Stephen. There's a question in the chat, which is, please clarify the advantage of Q-line versus traditional QKD. Is it just cost effective or is there more?
The way, I mean, what I believe is, so indeed the cost or the scalability, let's say, for a given cost, you can have more nodes is one thing, but also the fact that it does not use trusted nodes when you scale it to a network. Right, you're going to have a fully connected network without trusted nodes.
Great. Any other questions? No. So with that, thanks again, Mark. It's a great talk, and thank you. This is I think these kind of talks are a great contribution, especially I think they're quite the right level. So I really appreciate that.
Thanks a lot.
Physics was very limited, and the maths was kept outside. So it was good, and it was very focused on networks and the kind of advantages. So I like the level of the talk. So thanks a lot for the talk, and hopefully we'll see you at the QIRG otherwise.
Yeah. I have to say, this is probably one of the most technical talks I've been giving over the last couple of years.
Yeah, that's great. Okay,
but,
so that's thanks for that.
But I'm happy to recommend other people to delve into the details of the security proof, for example.
That's great. Thanks. Ronnie, do you have anything to add?
No, just again, thanks for doing the talk, Mark. I'll echo that. It was really good, and I think it was about the right level for this audience. And thanks for making it on time, because I'm sure lots of people have various other things on their schedule for the day. So it's nice to squeeze it actually in an hour. Wojtek, do you and I have any other announcements that we're ready to make in front of the group yet?
No. Everything's on the mailing list.
Okay.
Okay, great. Thanks, Mark, and thanks, everybody.
Thank you.
Bye.
Thanks, all. Stay safe, everybody.